This is part 2 of the rapid pre-processing tutorials. This tutorial will focus on delineating the watersheds in our region of interest. Open the project titled Australasia that was saved in the last tutorial. Before we begin working in ArcMap, we need to make sure that the ArcHydroTools Python toolbox is installed. If it is not installed, then please visit the yellow.esri.com link in the written tutorial. Select the version of ArcMap that you have installed on your computer. Then select the most recent version. Then select the 64-bit version. Download the .msi file and run the program to install. The program will install into the proper location on its own. Now that the ArcHydroTools are installed, let's import the ArcHydroTools Python toolbox that was included with the tutorial files. Download this, unzip it in a location that can be used in ArcMap for this tutorial and many other projects and tutorials. You will use these frequently. Go into your Arc toolbox, right-click Arc Toolbox, select Add Toolbox, navigate to the ArcHydroTools Python toolbox that you just downloaded, and add the toolbox. We will come back to these tools later in the tutorial. Now we need to obtain our flow direction and flow accumulation files. Fill the DEM by going to the System Toolbox, Spatial Analyst Tools, Hydrology, Fill. Use the Tasmania_DEM and default name. Compute the flow direction by using the flow direction tool inside the same hydrology toolbox. Use the fill output raster as your input surface raster and save the output as Tasmania_FDR in your Australasia.gdb. Next, compute the flow accumulation. This tool is also in the hydrology toolbox. Use the output from the flow direction tool as your flow direction raster. Save the flow accumulation output in your Australasia.gdb and name it Tasmania_FAC. After running the tool, change the color scheme by double-clicking on the color icon in the table of contents so that blue shows high accumulation and red is low. Next, right-click on the flow accumulation file in the table of contents and open the Properties window for the flow accumulation file and go to the Symbology tab. In the Stretch section, select Minimum to Maximum as the type. And in the Statistics box, select From Current Display Extent in the drop-down menu. Add a base map to your project and increase the transparency of the flow accumulation file to make it easier to view where major streams are actually located. The purpose of changing these settings will allow us to identify stream locations and to decide on a flow accumulation threshold. Now ready to delineate the watershed. Go to the ArcHydroTools Python now that it is installed and select Terrain Pre-Processing Workflows, Dendritic, Dendritic Terrain with Unknown Stream Location, -No FDR and FAC. The Dendritic Terrain with Unknown Stream Location -No FDR and FAC tool takes the FDR and FAC files created in the previous steps and uses them to create a river and catchment network at a user-defined resolution. Select the flow direction and flow accumulation files in their proper location. There are multiple ways to determine the number of cells to define the stream. One way is to use the Identify tool to find the accumulation at a given cell that you would like to set as the threshold. For this tutorial, we will use 130,434. This number acts as the threshold of cells that must feed into one location to determine a stream. The outputs for running the dendritic terrain with unknown stream location -No FDR and FAC should populate automatically except for the catchment flow split table. If they do not, or if there is an error, go back and make sure all of your files were saved in the right location and that your project was set up the way outlined in the Step 1 tutorial. For the catchment flow split table, you can simply copy the file location of the drainage line flow split table, but change the name of the file in the file path to catchment_fs, then click OK. The edges of the island are not included in any watershed because the elevation is too low and there are not enough accumulated cells to build a stream before the edge of the land. In most cases, you will likely choose a smaller threshold, which will typically allow greater accuracy and precision. If we were to run the dendritic terrain with unknown stream location, no FDR and FAC tool, with a smaller threshold, such as 50,000, more catchments and drainage lines would be generated. As mentioned before, you will need to decide the threshold of accumulated cells so that the sizes of the catchments and streams generated fit your specifications. Whatever the threshold is, we need to make sure the catchment-drainage line ratio is 1:1. Without doing so, Rapid will not run. Let's go back to our watersheds with the high threshold. Open the attribute tables for the catchment features and the drainage line features that were just created with the dendritic tool and check that the number of attributes in each feature class are equal. It is highly likely that the number of catchments will exceed the number of drainage lines. If the numbers are different, then right-click on the catchment feature class in the table of contents and select Joins and Relates, and then Join. Select Grid ID in the first drop-down menu. In the second drop-down menu, select the drainage line file that was just created and ensure that the third drop-down menu says Grid ID. Click OK. Back in the catchment attribute table, open the drop-down menu in the top left and select the Select by Attributes option. Enter drainage line dot object ID is null into the text box and click Apply. This will select all the catchments that do not have a stream inside it. Start an editing session and delete the selected catchments. Close the editing session and save your edits. Right-click on the catchment features in the table of contents, select Joins and Relates, and remove all joins. Verify that the number of drainage line features is equal to the number of catchments. The next step is to convert the projection of the catchment and drainage line feature classes. Use the Project tool and navigate the projection folders by clicking on Projected Coordinate Systems, World, WGS, 1984, Web Mercator, Auxiliary Sphere. You will now use these two projected rasters for the remaining steps of this tutorial, and all pre-existing rasters can be removed from the table of contents. The ArcHydro dendritic tool that delineated your watershed should have added a Hydro ID field to the drainage lines. It is best practice to check to ensure this field computed properly and that the type of the field is long. The catchment shapefile also needs a field that is recognized as an option of Stream ID in the Create Weight table from ECMWF Runoff tool. Add a field to the catchment shapefile and name it Drain Line ID. Set it to Long Type. The Drain LNID field that was just created needs to match the Hydro ID field in the drainage line shapefile. To do this, right-click on the catchment shapefile, Joins and Relates, Join, then in the Join data, match the grid ID of the catchments to the grid ID of the flow lines. It is best practice to validate your join to ensure all rows in your fields match. Calculate the drain LNID field in the catchments as the hydro ID from the flow lines. Be sure to remove all the joins. Check the drainage line attribute and make sure that the From Node, To Node, and Next Down ID fields are present. Next, calculate the Muskingum parameters accessed from ArcHydro Tools H&H Modeling Utility Calculate Muskingum Parameters. Use drainage line _ project as your input feature class. The K factor should be 0.35 and the X factor should be 3. Lastly, add the COM-ID field to the flow lines shapefile if it does not exist. This needs to be a long integer type, and copy the hydro ID into this field. You are now finished with Step 2 in the Rapid Preprocessing tutorials. Thanks for watching.